Hello, everyone. Welcome to Flow, our seminar series on federated learning, broadly constructed topics, including machine learning, distributed optimization, privacy, or even cryptography. So if you have any suggestions for speakers, please feel free to sort of send them to us, the organizers. Before we start the talk, so two quick administrative topics. So if you have questions during the talk, you're free to write them into the chat box. We'll read them out whenever like a good moment occurs, and then, or alternatively, you can raise your hand, and then one of the hosts will unmute you. And then this talk is being recorded and will be posted online. So keep that in mind if you sort of enable your video. So with that out of the way, it's really my great pleasure to introduce Anwar Hithnawi from ETH Zurich, who is an Ambizione Research Fellow and the research group leader at this institution, where she leads the Privacy Preserving Systems Lab. Her research focuses on data privacy, applied crypto and computer systems, and she completed her PhD at the ETH, and then she spent a couple of years as a postdoc at UC Berkeley. So more recently, Anwar's work has focused on security and systems challenges in deploying federated learning, and I believe this is what she's going to talk to us about today. So I'm really looking forward to your talk.
So thank you so much, Dan, for the introduction and the invite. So I'm very happy to be here today. Today we'll talk about the security and robustness challenges of collaborative learning paradigms. So just let me first set the settings of the different topics I will be covering today. So what I'm going to do in the first part of the talk, I'll give a deep dive on the robustness and security challenges of collaborative learning. And my intention here is to motivate how cryptography can help mitigate some of the integrity and privacy issues we see in these learning paradigms, and highlight the extent to which these cryptographic tools can be helpful. And in the second part of the talk, I will present Truffle, which is a system that enables federated learning clients to cryptographically prove certain properties about their updates to attain some form of attainable, meaningful robustness. Something I want to also clarify before I start my talk is that my background is in security. So my talk will reflect on my understanding of these issues from this lens. So machine learning algorithms continue to achieve remarkable success in a wide range of applications. Much of this success can be attributed to the availability of large domain-specific datasets for training machine learning models. So most of the success we have seen in the ML space is for tasks and domains where data is relatively easily accessible. This includes image classification or language models where we have available large public data that we could farm from the internet or even crowdsource it. However, many of the important questions we care about in society touch on private data that is difficult to access. This data currently lives in silos that are hard to access and also hard to compute across them. And there are more and more realization by governments and organizations that access to this data can bring large benefits to society, and that there is a need for legal frameworks, but also technical solutions that allow us to benefit from this data while preserving individual privacy. One promising technology for training ML models for settings of this nature is collaborative learning. So collaborative learning systems are learning systems that at their core aim to train machine learning models without the need to have direct access to data. The privacy benefits lie in the ability to retain data locally, and they are attractive for scenarios in which data privacy and liability are a concern. They also ensure data sovereignty and alleviate risk associated with large-scale centralization of sensitive data. There are many flavors to collaborative learning. The two prominent ones are decentralized learning and federated learning. So decentralized learning is a setup where we have a number of organizations engage in a secure protocol to perform a machine learning training on their joint dataset. This setup is particularly appeals to organizations that want to collaborate but can't due to privacy regulations, such as in the healthcare or the finance sectors. Federated learning, on the other hand, is a setup where we have a centralized service that aims to train machine learning models without needing direct access to the training data. So the training process is distributed across a large number of devices that collaborate to train a joint model through an iterative process that aggregate locally trained updates. So federated learning is especially appealing for organizations that coordinate large amount of devices containing privacy-sensitive data. And collaborative learning systems by default inherit all the known privacy and security issues in ML. Simply being collaborative does not make these systems more resilient to known attacks, both during the training and inference. In fact, their collaborative nature opens up new attack surfaces that are interesting to study and defend against. And this new aspect is what I want to focus on today. So I will start by discussing the confidentiality of input data, as this is arguably one of the main reasons why one wants to opt to use collaborative learning. Here, data holders want to assurances that their data is not exposed to the cloud server or any other party involved in the training process. So collaborative learning systems keep the data local and exchange only inferior update necessary for training the model. We would hope that this would prevent the cloud or other parties involved in the training process from accessing or stealing sensitive information. So although these updates contain less information than the raw data, they still can leak all sorts of informations. And it did not take much time till people started to craft attacks that allow the reconstruction of examples from these updates. So these attacks use techniques such as gradient invasion, inversion, gradient amplifications, or trap weights. So if anything I want to emphasize here is that decoupling data from training, so basically federation by itself, does not bring many privacy benefits. So to remedy these issues, these systems rely on encryption to ensure privacy of input data during training. So where decentralized learning often is used with MPC protocols, which ensures that no input or intermediate steps are revealed to any party during the training phase. So only the final trained model is released. In federated learning systems involve a large number of participants, so whereas currently MPC protocols cannot scale to these settings. So in FL, instead, we rely on secure aggregation protocols to bypass this performance bottleneck. In these setups, client encrypt their model updates, and the server can sum up the encrypted updates and can decrypt only the final sum. While this can leak information from the intermediate results, there are many privacy benefits to using secure FL. The system leaks nothing about users' input to the server except what the server can infer from the final sum. On a more general level, we have a variety of cryptographic constructions that can help us to mitigate different issues when it's come to the confidentiality of the input data, each offering their own trade-offs. We need to carefully tailor cryptographic solutions to our context, which often requires understanding of their cost models and adapting applications to be more crypto-friendly. So on the robustness front, collaborative learning can also amplify adversarial robustness issues known in the centralized settings. So several characteristics of collaborative learning can make the impact of these known attacks worse. These are attributed first to the open nature of these systems. So in collaborative learning, the training process is open and often involves a large number of participants, among whom any participant can act maliciously. Attacker capability are also different. So for example, the ability for the client to have a direct access to the model parameters allow for novel, stronger attacks such as model poisoning. In addition to that, attacker can persist throughout the training, allowing for stronger forms of adaptive attacks. Attacks in these settings are also harder to detect. As we rely on encryptions in these systems to preserve privacy, we cannot tell from inspecting the ciphertext if a contribution from the client is malformed or not. So I will briefly cover some of the attacks we have seen in these systems. So I will start by discussing data poisoning. So what are poisoning attacks? So poisoning attacks are train time attacks. So adversary manipulate the training data with the hope of changing the behavior of the machine learning system. These attacks were initially studied in the centralized ML settings, but they are especially concerning for collaborative learning because it only takes one compromised node in the collaborative learning system to embed a backdoor in the model. Initially, these attacks used strategies such as label flipping, but they became more and more advanced. So we now have trigger-based attacks that cause a system behavior to change arbitrarily when a specific secret trigger is present, while behaving as intended when the trigger is absent. These triggers can also be done by adding adversarial perturbation to the training data to cause targeted effect that is difficult to detect at this time. So federated learning is not only limited to data poisoning attacks, so they are also vulnerable to model poisoning attacks. So because the clients now have a direct access to the model parameters, here the adversary can craft malicious model updates. One example of these attacks is model replacement. So the adversary injects the desired target into their local model and then applies scale to amplify its impact. Model poisoning attacks are not limited to scaling, so also more advanced attacks in the literature work by changing the trained weights of the model directly. For decentralized learning, model poisoning to some extent is not an issue. So because carefully designed systems often as part of their secure protocol use cryptographic commitments, which is a cryptographic tool that ties a user to the input value without revealing the actual input. So parties commit to the input dataset and can prove that they use the same dataset throughout the computation, and which saves these systems from issues such as model poisoning attacks. These systems are, however, remain vulnerable to data poisoning attacks. So defenses for adversarial robustness proposed in centralized settings are interesting for collaborative learning, but also can be limited for several reasons. So the first direction I want to discuss here is the work that aim to design robust ML algorithms. So these algorithms can exhibit high cost. They can have a huge amount of linearity. So translating them to the encrypted setting can lead to a high cost. So it would be interesting to see more work on robust ML algorithms that are crypto-friendly. The second direction is detection mechanisms, but these often assume that, that we have a direct access to the data or the parameter updates that you can audit to filter malicious input. But due to encryption, most of these solutions can't be applied in collaborative learning. So the last direction is on the use of cryptography. So what role can cryptography play for robust ML systems? This is the least explored direction. Sorry. This is the least explored direction, but it's of a particular interest to collaborative learning because crypto tools for verification are also compatible with encryption. So we have very powerful tools that we can apply here. The main issue here is that traditional verification techniques implicitly assume that there is a pre-specified function f, the evaluation of which we want to verify. However, in ML, the function f is learned, and we don't have a ground truth to what we need to verify. But we also know that many of the adversarial robustness issues stem from maliciously chosen input data and not directly from deviating from the protocol. So the question here, can we verify something about the inputs that parties provide, such as the input data or the data distribution or the resulting gradients that would get us closer to our goal of robust machine learning? So there are initial interesting work in this direction, and it would be very interesting to see more work at the intersection of cryptography and machine learning that is targeted for robustness. So let me wrap up the overview part of this talk by emphasizing on key points. The first I want to highlight here is that federation does not by itself bring many privacy benefits. However, the use of these systems with encryption elevates the privacy benefits. The second is that we need more work on robust ML algorithms in the encrypted settings. both robust ML algorithms that are crypto-friendly, but also think about how we can put some of the powerful cryptographic tools to use to help ML robustness. And finally, it seems like a perfect solution to adversarial robustness in machine learning is an unattainable goal. We're now hitting another cat and mouse game with the poisoning attacks as well. So more powerful attacks bound to the current attacker threat model keep surfacing. So there is a more realization by the community that we need to go beyond only attack preventions. So if we can't fix learning algorithms, we need to think of risk assessment systems, also think of broader measures that can help minimize the consequences of these attacks at the deployment time. And one thing I want to just highlight here, as we design these solutions, we need to also consider, so for the very privacy sensitive sectors, these solutions need to also be privacy preserving. So that's basically the overview part of the talk. So before I switch to the second part where I will discuss a system, I can take questions if there's anything. The audience, okay, then now I'll switch to talk about Truffle. Here we look at how we can apply crypto verification to help with robustness. So Truffle is a system that allows clients to cryptographically prove certain properties or constraints about the encrypted contributions in order to attain some form of meaningful robustness. But to understand what constraints can be helpful for robustness, we first need to understand what vulnerabilities in the FL pipeline these attacks exploit. So let's set the stage of what we are trying to understand here. So in federated learning, the server sends the model to the client, which compute and update based on the local data set. Like client then send the update to the server encrypted using secure aggregation, and then the server recover the aggregation updates. And the literature has identified two types of adversaries attacks in federated learning. So data poisoning, which I just discussed recently, and also model poisoning. So let's try to attempt to understand why these attacks are possible in the first place. So the early type of model poisoning attacks in federated learning, which we refer to in the literature as model replacement attacks, worked as follows. So the attacker first trained a model using the regular optimization algorithm on both benign and malicious samples to create a model update that contains the malicious behavior, but also perform well on the benign task. Then the attacker scales its malicious update using a scaling factor to overpower the aggregation step, practically replacing the global model with their adversarial input. Well, this is not a new problem. So we know that linear aggregation rules are vulnerable to Byzantine behavior. This problem has been studied in the context of distributed systems, distribution machine learning systems. Here, a single Byzantine worker can force the parameter server to choose an arbitrary vector, even one that is too large in amplitude or too far in the direction from the other vectors. But this problem is also known and studied in security, particularly in the context of private data collection systems, where a malicious client can send the server an encryption of a large input or a large integer instead of the correct value. So in security, the general approach we take to mitigate or solve these issues is to rely on zero knowledge proofs. So the client proves that its submission is actually well formed. So what does a well-formed client submission in federated learning would look like, at least in the context of scaling attacks? So because these attacks rely on scaling a model update, if you inspect the updates of a malicious client, you would notice that they are much larger than the updates from benign clients. And therefore, the natural question is, can we prevent a model replacement attack by simply enforcing a bound on the norm of the clients? And indeed, for a model replacement attack, we see that norm bound can be actually effective. But would norm bound as well be as effective for other or stronger attacks we have seen in federated learning? So this has been debated in some of the recent work, each showing different results on the success of the norm bound preventing attacks known in FL. I think what is more important here is to try to understand better what enables these attacks. Yes, there is a class of powerful attacks that exploit vulnerabilities in linear aggregation rules and employing by employing scaling. And for these, a norm bound seems to be effective defense. But not all attacks exploit these vulnerabilities. Most advanced attacks simply exploit the nature of learning, making it harder to defend against. And this brings me to the long tail discussion, which is somehow inevitable. So modern datasets often follow a classical long tail distribution. A significant fraction of the data set consists of a rare, noisy, and atypical samples located at the long tail of the distribution. And now it's known to us that for large over-parameterized deep learning model tend to allocate a large part of their model capacity to memorize or learn these sparse long tail data samples to achieve good accuracy. So the long tail and model memorization in relation to privacy has been explored in depth because it is in part what allows the model to reveal sensitive training data. Specifically, rare training data from tail subpopulation are prone to memorization. But this learning behavior also has implication on robustness. So it seems it is what enables us to embed backdoors in the models from a few poisoned samples. So if models generalize well, then you would hope that your model should ideally not learn and embed a backdoor just from few poisoned samples. To see this more clearly, we analyze the effectiveness of norm bound on model poisoning attacks on different types of attack targets. So basically prototypical attack targets and tail attack targets. So for prototypical attack targets, even when an attacker is selected in each round, the norm bound prevent the model poisoning attacks. As opposed to prototypical attack target, attacks on the tail target does not manage to succeed after being injected attack on the tail target does manage to succeed after being injected after a few rounds. So even when a norm bound is in place, the model learns to associate the tail target with the malicious behavior. This suggests that it may be a good idea to suppress the tail. So several approaches to suppress learning of rare samples, such as regularization techniques, noise addition methods from differential privacy and compression could be used here. But unfortunately, it's a bit more complicated than this. So when we optimize for one thing, we can have unforeseen complication for other properties that we may care about. So we see that these solutions can also impact population with underrepresented attributes by increasing the performance gap of underrepresented subpopulations. This has implications for fairness. So today it remains opaque, the interaction between the model design choices we make and all these desirable properties that we may want our model to fulfill. And we need more work to understand these interactions. So I love to talk more about this topic, but these people have already done an amazing job highlighting these issues. So instead, I will leave these two great resources for you to check. So our understanding for this issue suggests that as of today, we don't have defenses against all attacks. Maybe even this might not be an attainable goal. But some measures we have are useful despite their limitation, and we need to proceed by strengthening our systems with these measures as we get a better understanding of these issues. This brings me back to the norm bound, so as a defense. So this measure is indeed helpful for a class of powerful attacks in federated learning. Let's proceed and see how we can actually transfer this defense to secure federated learning systems. So with this understanding in mind, now I will switch to talk about how we can actually enforce constraints in secure federated learning in a scalable manner while preserving the privacy of clients' contributions. Okay, so the goal we have here is to augment existing secure federated learning protocols with zero-knowledge proofs to allow clients to enforce constraints on model updates. So what we want here is we want our system to be compatible with existing secure aggregation protocols in federated learning, but also as these cryptographic constructions often introduce significant overhead, we want a design that allows us to handle the scalability requirements of federated learning. So to scale to a large number of clients and also cope with the update size that often consists of hundreds of thousands of parameters. So there exist secure aggregation protocols that are already heavily tailored to federated learning settings. In Truffle, we extend these existing secure aggregation protocols with zero-knowledge proofs to allow clients to prove constraints on the encrypted updates. So while a variety of zero-knowledge proofs exist, the challenge here is to apply zero-knowledge proofs in a way that preserves the scalability requirements of FL. So before I dive on how we do this, let me first give a quick recap of secure aggregation protocols. So the state-of-the-art secure aggregation protocols for federated learning is based on canceling nonces. So in essence, each client encrypts the values by masking them with a random nonce that cancels out when clients' value are added together. So there exist protocols that provide efficient subroutines to create such nonces between clients and expand them to a large vector, but this aspect of the protocol I will not cover today. So after masking, each client sends its encrypted update to the server, and once the server aggregates the encrypted updates, the masks cancel out, and the server can recover the sum of the updates. And the question now, how we can prove constraints on top of these encrypted updates. So to provide zero-knowledge proofs for constraints on updates, the client would need to prove that the update was masked with the correct canceling masks, else they can cheat. So providing such a proof is actually expensive and not practical for settings like FL. To circumvent this issue, we replace the masking procedure with a cryptographic commitment that takes a value and a random nonce as an input. So the hiding property of the commitment ensures that the server does not learn the value as before. However, in addition, the binding property ensures that the client can't change the value inside the commitment at a later stage. So now a client can provide zero-knowledge proofs that the commitment is well-formed and the proof statements on the committed values. So by using additive homomorphic commitments, we can as well support secure aggregation at the server. So the additive homomorphic property allows to combine two commitments such that the result corresponds to the sum of the committed messages and the randomness. So similar to the masking approach, the server can aggregate the commitments and the randomness cancel out. And in Truffle, we employ Al-Gamal commitments, which then allows the server to reveal the aggregated updates by solving the discrete log. So with this, Truffle can support arbitrary constraints on client updates using non-interactive zero-knowledge proofs. So we provide efficient implementation and optimization for the L-infinity and the L2 norm-bound constraints. So for the L-infinity norm, the clients have to prove that each parameter is within the L-infinity bound. So we use the bulletproof zero-knowledge proofs that support efficient per parameter range proofs and are compatible with Al-Gamal commitments. These proofs also support patching of multiple proofs into a single proof, making them particularly bandwidth efficient for large vectors of values. For the L2 constraints, we further require a commitment to the square of each parameter. So to ensure the sum of squares is bounded, the clients additionally proves in zero knowledge that the commitments are well formed, that the squares are correctly computed, and the sum of committed square is actually bounded. So despite having a protocol that is optimized to the problem we have in hand, still enforcing these known constraints on a high dimensional vectors with several clients raises many scalability challenges. So to address this issue, we ask if we can reduce the number of required proofs while maintaining the same level of security. And to do that, we introduce several optimizations that could help with the scalability of this approach. And I will briefly discuss two of them here. So we observed that the attacker needs to scale a significant fraction of parameters to succeed. So this means that the server can check a small randomly sampled fraction of the parameter and still detect attacks with a high probability. In fact, we show that checking less than 1% of the parameter is sufficient giving us a huge speed up. So we use probabilistic checking. Here, the client still need to commit to all values, but then we have an additional round trip for the server to ask for range proofs on only certain parameters. For the L2 constraints, we have to ensure no overflow happen during the bound computation, which require a loose bound for each parameter. So instead, we propose to use L2 norm preserving compression technique to reduce the number of updates parameter that the server then need to verify. So for this, we use subspace machine learning, where we project the model parameters into a space of a smaller dimension. So each client trained the model in this subspace using a regular optimization algorithm. And the key is that the projection matrix is orthogonal, so which means it preserves the L2 norm. So the client then proved the L norm for this lower dimension subspace using less parameter. So now let's have a look at the performance numbers in the end-to-end system evaluation. So we first look at the setup where we have 48 clients trying to improve a CFAR model that has 270,000 parameters. So for the L2 norm constraint, we can observe that our optimization reduced the total training time by a factor of 10, with a slight reduction in accuracy. For the L infinity constraints, we reduce the total training time by a factor of 17 with probabilistic checking. The bandwidth, on the other hand, cost is actually dominant by the size of the commitments. So with the L2 compression, we can reduce the bandwidth by a factor of roughly 7. So next we show the results for a language model that consists of 800,000 parameter on the Shakespeare dataset. Here we can see that the training time overhead of the optimized version of Truffle is only a factor of 1.3 compared to the plain text. This is because local training at the client is more resource intensive for the language models in compared to the cryptographic operations on the updates. So we have now the preprint of Truffle available online. We also provide the code for the analysis and Truffle protocol in GitHub if you would like to check them. And that brings me to the end of the talk, and I'm so happy to take questions. Thank you.
All right, thanks a lot for the very nice talk. So let me start off with a couple of questions, and then maybe the audience can also post them in the chat or raise your hand so we can unmute you. So I mean, in the experiments that you mentioned, what was the kind of the data splitting like protocol? So basically, did you sort of split data randomly, or did you sort of partition it across classes, or I don't know, was there any, like, do you assume you have like random access to like random sort of access to data, or is it sort of more personalized?
I think what we did, we tried to make the data non-IID. We just took one of the data sets. I can't recall, but I don't think this really will impact the performance numbers we have.
I mean, I think what you're running is kind of one-to-one with sort of a like normal sort of FL application. It doesn't seem to me like you're making. I mean, there isn't that much approximation, but it would change, for instance, the accuracy. Like,
I see. I see where you're heading. Yeah. Okay. Yeah, I see.
So I guess, I mean, if my question, you can just rephrase my question. Like, did you assume the data was IID or non-IID?
We made sure that the data is non-IID. So the data is
non-IID. I mean, I had two questions from kind of earlier in the talk, and like one is like, are you aware of any sort of attacks on federated learning protocols in the wild? Like, has any, and I mean, from the security community, is like, has anyone actually tried to break federated learning? It was done by Google or something in the wild, or like, are you aware of any such results?
I'm not aware of any, but that does not mean that. I mean, we need to design our systems to be more resilient, and we need to anticipate that these issues can happen. So that's
yeah.
That's my
yeah, and I mean, you also mentioned, I think very early on, you had a couple of very, I think on the bottom of the slide, you had a couple of examples like of very cool sounding crypto techniques, particularly like in interactive proofs for like distributed ML or something like that. I mean, how can you just point out, maybe like, can you explain if maybe the audience should be aware of these?
I think they're really interesting. So what they're trying to prove, prove whether something about the data distribution, whether you're within the data distribution or your adversarial. I'm thinking that this actually can be helpful for robustness. Still, it's very expensive, but the ideas proposed there are, at least for me, seems to be very interesting. So, because we need to think of if the issues does not really arise from deviating from the protocol, what else we could verify? We need to think of what type of constraints or properties we need to verify about the input data or the data distributions. And I think that requires, because I mean, we can know how to verify things, but it would be very helpful to understand as well from the ML community what would be the good things to verify about data distributions. But this, you hit the distribution shift challenges, then again, can we actually tell adversarial distributions from a normal natural distribution shift? I mean, these papers discuss all these issues, and I think they're really, I would check them. There's no harm in that. They're interesting.
Are there any other sort of cool results that you sort of saw maybe from the applied or theory community, besides ROFL, that we should, I mean, people who kind of attend
not that I'm aware of. I think this is the first line of work that I'm aware of, that trying to verify certain properties about the distribution that comes actually from cryptographer, but maybe I have missed some work. So these are actually, yeah, I don't want to say, I think those are the ones that I'm aware of, and I think they're interesting.
And I think there is actually quite an interesting question. So I think we can unmute Waleed.
I can't hear.
I asked him to unmute. Maybe he's away from his computer. Otherwise, I can. He cannot talk. Okay, so I'll read out your question. So you mentioned. So the question goes. You mentioned you use bulletproof for the range proofs. While bulletproof is efficient for vectors of large dimension, it still has to scale with D, which I imagine is the dimension. Is there a particular reason the scheme was used rather than a ZKRP system such as ZK snarks, which can be more efficient for large vectors?
So it depends what you need to prove. These seems to be very efficient for if you want to prove range, and this is what we're trying to prove here. So if you want to prove other properties, maybe you need to consider different type proofs, but those are heavily customized, or they perform very well if you want to construct range proofs, which is the bound basically in our case. We looked at, I think in the paper, we have a bit of discussion on how other proofs could actually, the performance characteristic of other proofs, generic as NARCs and so on. But because we're proofing range, this seems to be very efficient to the type of proofs we actually consider.
All right. At least your answer sounded very convincing to me, and I think Waleed also is very happy. So.